all algebra, this section. And if you have a previous experience from calculus, that gives something different. Now, what is going to be this one? Remember we talk about those, if you have a relationship that introduce a recursively defined sequence, this equation is referred to it as a recurrence equation. We talked about it the other day. So the title is going to be, so that you are not going to be confused, is going to be solving. Okay, solving a linear recurrence relation or equation. Recurrence. Okay, recurrence relations. So there is going to be a sequence involved. The general term of this sequence is given to you as an equation, and you are going to find it. And we give you this expression, general linear recurrence, on the test, so that you are not going to be confused. Because there is going to be no induction in this one for a change. So what is this relation is going to be about? The definition is like a linear differential equation, if you are familiar with this. If an, as usual, is going to be sequence that's going to be defined recursively, is a given. Okay, is a given sequence that's defined, that is going to be defined by this equation or relation, by the following relation. So relation is going to be recursively defined. Okay. Now what is this relation? You see, you have a special format. An is equal to the a number, we call it a, times its previous term, an minus 1 done. Okay, 2, 3, 4, 5, plus another number, b, times the other terms, 1 done, an minus 2. Okay, so you must end up with n minus 2 in this case. In general, you can go on. You can go with the next time is going to be can minus 3 minus 4, but we are going to consider up to the second. In general, if you can do the up to the second, then you can do it up to the third, to the fourth, etc. There is going to be sometimes a function here, f of n. Okay, so you have your general sequence. It's just a combination of a linear combination. We call it 2, 3, 4, 5, 6. It's a linear combination of two of its period terms, if you like. And this is going to be the equation where, okay, it's going to be an. Of course, this n would start with, because you have the 1 and we have the 2, and if you want, it's going to be starting from 3. Okay. So this, we just explained that this a and the b must be a constant. Okay, where a and b are just numbers, are constant. Okay, if this is going to be the case, then this relation, okay, then the relation or the equation, okay, this relation is going to be called, okay, this relation is going to be called a second order. The second, because you go up to the second here, is going to be a second, okay, a second order linear, second order a linear recurrence relation or equation, recurrence relation, recurrence relation with constant coefficient, because a and the b are constant. Because if they are not going to be, the situation would be different. So with constant coefficient. constant coefficient. So this is going to be what we have. Okay, n is in terms of the an minus 1 and an minus 2. Those coefficients a and the b are numbers. If you continue, if you get the next term is going to be an minus 3. If it's going to be an minus 3, it's not going to be the second order. Okay, then the next one is going to be a third order, if you like. If you go up to the fourth, the fifth, the sixth, but if you can solve up to the second, then you can do the other one too. If you have the experience from calculus, the similar one that we have in calculus is that you are going to start with a derivative of a function. So this would be y double prime equal to the 3y prime plus 5y, if you like. You know that an equation that contains the function and its derivative is called differential equation. And that would be called linear differential equation. You know that there's a course that you get and you can solve those equations. They are a similar idea, these two together, but nothing to do, it doesn't matter. You don't need to know those to get these numbers. Okay, so let's get the example to see what we are going to have. So for example, this is one of them. You start with the an equal to 3an minus 1, okay, minus 4an minus 2. Then you have a function of n, like plus 3n minus 5. Okay, if you compare it with whatever we did, so this is a constant, so a is equal to 3. This is another constant, so b is equal to the negative 4. And this extra term is going to be your function. Okay, so this relation is a second order, Okay, second order, as we talk about it, linear recurrence. Okay, linear recurrence relation that we are going to have. Okay, any question? Now, the case that we are going to be interested in is that there is not going to be an extra term. If there is no extra term, even in general, if you want to solve this one, you have to solve this case first, you see. If there is no general term, we say this equation, this relation is homogeneous. Okay, so if fn is equal to 0, no extra term, then your equation would be this one. Your general equation would be, you start with the sequence an is going to be simply a times an minus 1 plus b times an minus 2. You see, this is going to be your equation now. This equation is going to be called, okay, we call it again a second order because we go up to the second. So it's going to be a second. Okay, it's going to be a second order linear. Now the expression is going to be the use homogeneous. Linear homogeneous. Okay, homogeneous recurrence. That's it, a recurrence relation. This is the one that we are going to work on. It can be classified, and it's going to be quite a lot of the different cases, but we are going to be interested in this format. Okay, so if an is equal to 0, so in that case, you are going to have a homogeneous recurrence relation. Okay, you have one example problem in your book that they give you a set of relations and they ask you to determine if they are linear homogeneous relation. Okay, so let's check that example or the similar one. So the example is going to be, we want to determine, okay, determine if the given relation okay, determine if the given equation in this case is of those format, is going to be a linear of this type that we talk about it. Okay, a linear recurrence relation. Linear recurrence relation. Okay, I'm going to write it down one by one. If it's not, you just tell us what's wrong in that equation. The first one. Okay, the first one is this one. AN equal to 3AN minus 1. Okay, minus 15 AN minus 2. See, nothing wrong with this one. It's just the standard one that we talk about it. Because you have a number times 3 times AN minus 1 and the 15 times AN minus 2. You have the N minus 2, so this is a second order. Okay, second order recurrence relation with a constant coefficient, which is also a homogeneous one, if you like. Okay, so let's run with this one. Any question? I just put some famous one that we're going to work with. So let's get the second one. The second one is the Fibonacci equation. Remember Fibonacci? Fn equal to the Fn minus 1 plus Fn minus 2. That's a linear equation. It's going to be linear equation with a constant coefficient because the Fn is defined in terms of the two previous one. Okay, so that is also fine. Get the next one. There is one case that you're going to use this one. You want to make sure you are going to be okay with it. You see 7bn minus 2. You see, this is also fine because you have the n minus 2. It doesn't matter that you don't have a bn minus 1 because you can write it down. You see, look at this one. So this is fine because if you like, you can think about it as, okay, you can think about it as this one as a bn equal to the 0 times bn minus 1, okay, plus 7 bn minus 2. So as long as you have the bn minus 2, okay, as long as we have a bn minus 2, so we be fine here to get these numbers. Okay, any question? No.
What if it was the other way around and
Which
the
one?
bn minus 2 was 0 and
No,
bn?
that won't be a good one.
Okay.
Because if you don't have the bn minus 2, then you cannot say that this is a second order.
Okay.
It would be first order if you like. Okay, but it's not going to be second order. So it's not going to be part of our pattern here. Okay, so the different one is this one. Okay, this is going to be an equal to an minus 1 but squared. Okay, plus an minus 2. What's wrong with this one? Any suggestion?
The coefficient isn't constant.
No, it is constant. The coefficient is 1.
Oh,
And the one, there is something else. What is different?
It's got an a squared.
That's it, the power. You see, we talk about it, we want it to be a linear equation. When it's going to be linear, you cannot have the power here. Okay, when we say it's a linear combination of x and y, so you mean 2x plus 3y. You cannot have the power for the linear. Okay, so in this case, this is not going to be of the group that we talk about it. Okay, it's not a linear equation. It's not a linear equation because you cannot have the power here. Okay, so this is it. Now, what's wrong with this last one? The last one is Bn. Okay, it doesn't matter, you can have Bn, Cn. Is n times Bn minus 1. Okay, plus 7Bn minus 2. What's wrong with this one?
Coefficient on the Bn minus 1 isn't constant.
That's it, it's not constant. And since we only talk about those constant coefficients, so in this case, we are not going to consider this one of a group, okay? So in this case, we have a non-constant. Okay, we have a non-constant coefficient, which is no good. Okay, just want to make sure you get the idea of what you are going to know, what you are going to have to get these numbers. Okay, these numbers out. Okay, any question? Just make sure you get this one right. I have more rooms here. Okay, so this is going to be a situation that we are going to have for these type of problems. Okay, so the next question is going to be one of these equations would be given to, and they ask you to find the an. Okay, you see previously when it was only one, you see, if you have after the n minus 1, we just did it by induction, remember? But for the second order, it's not easy to do this type of inductions. You did somehow this type of equation before, but remember we gave you the solution and then you confirm it by a strong induction. So we get it to on the final again. We give you the solution and we ask you to confirm it, but this one is different. No solution would be given to you. You have to find the solutions, okay? So just make sure they are going to be different. Now, how are we going to solve it? You see, in order to solve it, we are going to use, I just then refer to the calculus so that you know what I'm talking about. You see, look at this one, the case in calculus. The case in calculus, this type of equation is going to be this one. See, they start with a y double prime, second order. This is going to be equal to the what? This is going to be equal to the, let's say, 5y prime. 5y prime over here, and this is going to be plus or minus. Okay, it's going to be minus 6y. This is calculus. In calculus, this is called a differential equation of a second order because you get to the second derivative. So again, this is called a linear differential equation with a constant coefficient in those courses. And if you want to solve it in calculus, the way we're going to do it, you see, you are looking for a function that the derivative of the function is a kind of a multiple of a function, if you like. So for example, it can give us a function whose derivative is the same as the function in calculus. Not, of course, 0. Can give us a function whose derivative is the same as the function. In calculus, I'll give you one. How about e to the x? Derivative of e to the x is just e to the x. You see, this is one of them. Can you give us a function whose derivative is twice of the function? A function whose derivative is twice as the function. How about e to the 2x? Yes, you know that exponential function never change. Derivative would be e to the 2x. You have to multiply the derivative of the 2x. So that gives it 2e to the x. Okay. So it e to the 2x, of course. And you can continue. In general, if you want to find a function whose derivative is r times the function, so that gives r e to the r to the x. So this type of the equation must be satisfied by this group of functions. Okay, this is the way we do it in calculus. We say, oh, the solution must be something like y equal to the e to the rx. Then we try it, we substitute to get the same result. You know, in case you have done it, but if you don't, forget it. So let's go back to the one that we have over here. So let's see. I'm going to use the same idea, but it doesn't matter if you don't know it, because this is the modern version of that one. So what is the plan? The plan is how we're going to solve these equations for us, okay? So solving this type of equation, linear, recurrence relations. We are going to solve only homogeneous one, okay? Homogeneous one, I didn't write it down. With that constant coefficient, okay? Nothing else. So let's, one of them is given to you, okay? Suppose this relation is given to a relation okay, a relation what? an equal to the a times an minus 1 plus b an minus 2, okay, is given. This is given to you, okay? Now, what we're going to do for this type of the equation, you see, in the case of the differential equation, it was e to the something. In this type of the relations, you can assume that the an is a constant number, okay, raised to n maybe, to get these numbers over here. You see, because your relation in this case is going to be something like 2 to the n, 5 to the n, 7 to the n, or you can force it to be these type of solutions. Okay, so what we are going to do is, so suppose this equation is given to and assume that, because we have that experience from the calculus, we assume that an equal to the r to the n, r is a number, is a solution, okay, is a solution of the relation, of the relation, okay? So if you assume that this is a solution of your relation, this solution must satisfy your equation, okay? So you can substitute it. Therefore we have substitute. So you get this equation. Substitute here, an is r to the n, so it's going to be r to the n equal to a times what? An minus 1. If an is r to the n, so an minus 1 would be r to the n minus 1. R to the n minus 1. Plus b times what? An minus 2. If your an is r to the n, so an minus 2 would be r to the n minus 2. R to the n, okay, n minus 2. Any question? So we force the solution to be r to the n, and we want to see what would happen if we force this condition. Okay, let's simplify this one. You have the powers of r. The lowest power of the r is going to be n minus 2. So I'm going to divide everything by, so divided by r to the n minus 2. Okay, that's going to be r to the n minus 2. And this is going to be divided by r to the n minus 2. So this is r to the n. The difference is 2 units. So that gives r squared. Okay, that gives r squared. And n minus 1 and n minus 2, the difference is 1. So this would be a times r when you simplify it. And this part, these two would cancel out. Let's say this two would cancel out. So the leftover would be just b. See? So this will tell you that r to the n is going to be solution of your equation if that r would satisfy these equations. or you can move everything to one side if you like. So that gives r squared minus ar minus b equal to the 0. You see? So what we did, we changed the given problem into algebra. So this means r to the n is the solution of the relation if and only if r is going to be a solution of this quadratic equation. Okay, so you find a kind of one-to-one correspondence between these ideas. So this is what you did. Therefore, you can claim that an equal to the r to the n is a solution. Okay, it's going to be a solution of the relation, of the linear relation, of the relation, okay, of the relation, if and only if r is a solution, okay, is a solution of the equation, okay, of the quadratic equation, which is r squared minus ar minus b equal to the 0. Okay, so if you can find the r, then you come back, you substitute, you get the solution of your relations. Okay, this equation, this last one, I'm going to call it a star equation. This star equation, call it characteristic equation. It's the same as the expression that we use in calculus, okay, or in differential equation. So a star is going to be called, okay, a star is called the characteristic equation. Okay, this is it. It's going to be called a characteristic equation. It's going to be characteristic equation of the given relation, of the given relation. Okay, so quickly we change the given problem into the algebra problem, if you like. Okay. Now, you know that in order to solve this equation, you're going to have three cases. You may get two solutions. Okay, two different real solutions. You may get only one solution. We call it repeated solution because it's a two solution, but we call it one. Or you may get complex solutions. Okay, in your case, you're just using real numbers. So it's going to be two cases. The complex is not a big deal. There is one problem in your book. They talk about it, but you are not going to use it. So we are going to only consider two cases. Okay, so say, oh, there are two cases. There are two cases. Remember, the plan is to find a formula for the solution of the original one. Okay, so what's going to be case one? Case one is you solve this equation, we get two solutions. Okay, so we call it distinct. Okay, we call it distinct roots or solutions. Okay, that's going to be case one. So in this case, you solve this quadratic equation, you get two solutions. We call them R1 and R2. Okay, so this is going to be the case if R1 not equal to the R2, distinct, are going to be R2 distinct solutions. Okay, solutions of the characteristic equation. Okay, two solutions of that characteristic equation, which is the star equation. If this is going to be the case, You see, R, in that case, R1 to the n is one of the solution, and R2 to the n is going to be other solution. So we get two solutions. And then we have something with linear algebra that will tell us that any linear combination of those two solutions are going to be solution again. So we just, we briefly, we put them together. You don't need to be familiar with those. So if R1 and R2 are going to be two distinct solutions, then the general solution of your equation is AN is equal to C1, a number. R1 to the n, one solution. C2, R2 to the n is going to be the other solution. This would be the general solution of your equation. Okay, this is going to be the case. And this is going to be the general solution. Is going to be the general solution of the linear, linear relation that we start with. Of course, this is where C1 and C2 are just numbers, okay, are constant. They are going to be constant numbers. So you have infinitely many solutions because you can replace the C1 by C and C2 by any number you like. But they usually give you an extra condition. When they give you extra condition, then you'll be able to find the C1 and C2. So you're going to find a unique solution for us. But this is generally what would happen for this one. You are familiar with the linear algebra. We have something that we call it a basis. So this R1 to the n and R2 to the n is going to be a basis for the vector space of the solution of all the equations, okay? And then when you have a basis, the linear combination of the elements of the base would give you, the AN. But otherwise, this is it. We can prove it for you. So we are going to use it. So this is going to be your job. So you have to find the characteristic equation first. You say this is it, R squared minus AR minus B equal to 0. Then you solve it. You solve that equation if you get two solutions. You are going to call one of them R1, the other one R2. Then you bring it here. You substitute, that gives you the general solution. But it's usually giving you some extra condition. Then you substitute those extra conditions, you get the C1 and the C2, and then you have a particular solution. I give you the second case too, then we give you example, okay? So that is the case that we have, we have two distinct solutions. Any question? So what's going to be case two? Case two is this equation, you want to solve it, you get only one solution. You know that, the discriminant would be 0. You have, in fact, two solutions, but they are repeated, if you like. So that is going to be case two. Then you have to modify those. Okay, the first case. And we have a new formula. So what's going to be case two? The case two is, we call it repeated solution. Repeated roots or solutions. Repeated solution in this case is going to be easy. So if you try to solve that equation, but you get the same number, R1 is equal to the R2. You're going to call it the R. Okay, if this is going to be a repeated solution, is going to be a repeated solution of the characteristic equation. Okay, of the equation. Okay, of the equation star or characteristic equation. If this is going to be the case, then your general solution this time is this one. Make sure you don't miss it and write it down correctly. You get the an equal to the C1 r to the n is the first one. But as in calculus, we can prove that the second one is going to be n times r to the n. So it's going to be C2. Okay, this is the first one. The second one is going to be C2 times n r to the n. Okay, instead of r1 to the n plus r2 to the n, in this case, one of them is going to be r to the n. The other one would be, okay, n times r to the n. Okay, and this is going to be true for, depends on the n. If the n starts from 1, it's going to be n 1 to 1. So in this case, is going to be the general solution. Okay, the general solution of the given linear relation. Linear relation. That's it. Two different cases, okay? If they are going to be distinct, for each number, you see, you get r1 to the n, r2 to the n. The linear combination is the solution of your equation. If you get a repeated solution, one of them is going to be C1 r to the n, but the second one is n r to the n. They can be proved. You know, you can go back and substitute in the equation. They would satisfy. In calculus, we get the first one is e to the x. The second one would be x e to the x. But it's going to be a similar one over here. Okay, so that's it. This is the way we're going to do it. This method would give you up to the second order. You can have the third one. If you have a third order, then characteristic equation would be more complicated. It's going to be cubic one. Then you get three solutions, for example, R1, R2, R3. It's the same thing. If they are going to be distinct, your solution would be R1 to the n, R2 to the n, R3 to the n, okay? So that's why if you can do the second order, then you can copy this one for any other order that you like. Okay, that's the instruction. Any question? We are ready to do it. We give you two questions, one each. Okay, so I give you three examples. The third one is going to be Fibonacci numbers, which is a little bit different, but otherwise it's a straightforward problem. And then you're done. Okay, any question? So let's do it. That's it. Example. We want you to solve each. It's the way we are going to give it the problem. Solve each linear, we emphasize. Linear recurrence relation. And you know that this is coming from this section. There you are, the first one. AN equal to, AN is equal to the what? It's going to be equal to the AN minus 1 plus 2 times AN minus 2, AN minus 2. And they like the n to start from, they like to start from 2 to 3. So they have to give you A0 in this case. A0 is given to you, and the A1 would be given. Okay, these initial conditions would be given to you. That's it. Okay, you have to get the characteristic equation first. Some people, they substitute, they put AN equal to R to the N, they substitute it, but you don't need it. You can quickly find the characteristic equation as follows. Okay, so there you are. Note that the characteristic equation, the characteristic equation of the relation, okay, of this relation is, you see, it's very easy to find. You start with the r squared equal to r squared equal to, you see, whatever coefficient is here times r. It's a 1 times r. I write it down so that you know it's going to be 1 times r. You see, you start with the r squared, you reduce the power. It's going to be r to the first plus 2 times r to the 0. R to the 0, I write it down so that you know what's going on. But r to the 0 is 1. So you have r squared equal to the r plus 2. That's your equation. Okay, start with the r squared. Whatever coefficient is going to be coefficient of the r and the constant. That's it. It's equal to, of course. So you move it to the other side because you want to solve this equation. R squared minus r minus 2 equal to the 0. Factoring to solve it. Be careful, you need two numbers. So it's going to be r minus 2 times r plus 1 equal to the 0. So you're going to have two solutions. You can call one of them r1, the other one r2, it doesn't matter. So r1 is equal to 2, one solution. And r2 is equal to the negative 1. Okay, the other solution. Any question? As you can see, they are different. So the R1 is not equal to the R2. So what's going to be your general solution? AN is equal to C1 R1 to the N plus, okay, plus C2 R2 to the N. Substitute. So your AN is equal to C1, you don't have the C1, it's going to be C1. Is C1, okay, R1 to the N is going to be C1 times 2 to the N plus C2 times R2 to the N. R2 is a negative 1. Negative 1 to the N. Okay, so this is going to be your general solution. So the general solution, AN is equal to the C1 2 to the N plus the C2 negative 1 to the N, but you have to tell us the N. Since you have the A0, so this would be true for N equal to the 0, 1, 2, etc. Okay, so this is going to be the general solution. The general. Okay, general solution. Any question? No, you check to see if you have initial condition, you continue. Otherwise, you stop. We usually give you the initial condition, okay? But what is your initial condition? The initial condition is that you see A0 is equal to 1 and the A1 is equal to the 8. So that would be given to order in order to find the C1 and the C2. Okay, so we are not done. So, oh, but I have the initial condition. I have the fact that the A0 is equal to 1. Okay, and A1 is equal to the 8. So go back over here. Substitute to get the relation. That give you a true relation in terms of the C1 and the C2. Then you have a system of two equations, two unknown. You can find the C1 and the C2, okay? So A0 equal to 1. So you go to this equation, you replace the n by 0. Okay, if you replace the n by 0, so that give you A0. Okay, I'll write it down for you. Okay, it's going to be A0 equal to C1 2 to the 0. Okay, plus C2 negative 1 to the 0. Okay, if you substitute, your A0 is 1. So these are going to be, okay, these are going to be 1, each one of them. We don't usually write it down. Just we do it right away. Okay, the A0 is 1. So the conclusion is going to be, we get the C1 plus C2 equal to 1. So this is one equation or one relation between the C1 and the C2. Any question? So you repeat it for this one. Replace n by 1. You substitute that, give you the second equation, then you can solve it. Okay, so we continue. Say we have what? We have the A1 equal to the 8. So go to the general solution and replace the n by 1. Replace n by 1, that give you A1. So it would be 8 equal to. 8 equal to is going to be C1 times 2 to the first power, okay, plus the C2, negative 1 to the first power. So that give you 2C1, and this is going to be minus C2 equal to the 8. Okay, you substitute, you replace n by 0, A0 would be 1. And you replace n by 1, so A1 would be 8. So put them together as a system of two equations, two variables to take care of it. Okay, any question? So let's put them together. Get that last part. So this is it. What you have? You have from the first part, we have the C1 plus C2 equal to 1. And from the second part, we have 2C1 minus C2 is equal to the 8. Okay, addition method is the best method to take care of these. So if you add them together, the C2 would disappear. Okay, then you have 1C1 and 2C1 that give you 3C1. And this would be equal to the 1 and 8 would be 9. So C1 would be equal to 3. Any question? So you put it here, it doesn't matter the first or the second equation. So I put it to the first one, so that give me 1, 3 plus C2 equal to 1. So the C2 would be 1 minus 3, which is a negative 2. So the C2 would be a negative 2. Any question? If not done, you have to go and give us the final answer. So what's going to be the final answer? AN is equal to C1. C1 is 3 times 2 to the n. Okay, and then the C2 is going to be minus 2, and what was the other solution? The other solution was a negative 1. Negative 2 times negative 1 to the n. And you have to tell us the n can be 0, 1, 2, etc. So that gives you the final answer. Any question? You can check it for yourself. See if you present by 0. So that gives 3 minus 2, which is 1. A0 is 1. At least you check to make sure you get it. You get it right.
Can you go
Yes.
over where you wrote the equation for A0
Yes.
and A1
Yes, you see.
on the very bottom there?
You see, that's going to be 1. So you have the A0 equal to 1. And this is your general solution. Okay, replace n by 0. When you replace n by 0, you can say 1 equal to. Okay, but I'll just explain it. So replace n by 0, that's going to be A0. It's going to be C1 2 to the 0. And the C2 negative 1 to the 0. Anything to the 0 would be 1. So you have the A0 1, and it's going to be C1 plus C2 equal to 1. Then you repeat it for A1 equal to the 8. Replace n by 1, so 8 equal to. 8 equal to the 2C1 minus C2. Then you put them together, and then you solve a system of the equation. Any question? So that's case 1. So the case 1 that we have two different solutions. Okay, so we have another case. Another case is the one that is very unique, the second one. Then you get a case that your characteristic equation would have a repeated solution. So Let's check another one here to get this number. So what's going to be case 2? So in case 2, we want to solve this relation for us, okay? Solve an equal to the 4 an minus 1, okay, minus 4 an minus 2. This is given to you, and they want the n goes from 2, 3, etc. So they are going to give it the a0. A0 is equal to 1, and the a1 is also given, is equal to 3. Okay, this is going to be your relation. So we can do this one quickly. Okay, are you ready? Characteristic equation first, solution. So I just remind you that the characteristic the characteristic equation of the relation is remember the way we do it, it's going to be r squared equal to 4 times r minus 4. That's going to be your characteristic equation. Okay, you start with the r squared because you have the second degree, and then you go down. This would be r squared, this is going to be 4 times r to the first, and this is going to be just a constant. That's it. You move it to one side to solve it. R squared minus 4r plus 4 equal to the 0. And you factor it, you find out that you have a repeated solution. So this would be r minus, what's that? R minus 2 times r minus 2 equal to the 0. Okay, so we have a repeated solution. So in this case, this is it. So your R1 is equal to the R2 and is equal to 2. So you have a repeated solution, so you may call it R equal to 2. R equal to 2 is a repeated. Okay, it's going to be a repeated solution. A repeated solution. So what's going to be the general solution? Remember, for the repeated one, the general solution is going to be a C1, okay, R to the N plus C2 N times R to the N. You substitute. So AN is equal to C1 2 to the N plus C2 N times 2 to the N. N times 2 to the N. Okay, this is going to be an equation, and this would satisfy for n equal to the 0, 1, 2, etc. Okay, but we have initial condition. So your initial conditions are, okay, but that's it. We have a0 equal to 1. So replace n by 0 in this equation. So that gives a0, which is 1, equal to the c1 2 to the 0. And this would be 0 because of the n here. So it's going to be c2 times 0. Okay, so in this case, this would be out. So that would simply give you the c1. Because 2 to the 0 is also 1. Okay, so automatically you are going to have your c1. Okay, you have one more. Your second initial condition is that a1 is equal to 3. So go here, replace the n by 1. So that gives a1, which is 3, equal to n equal to 1. So that gives c2, 2 to the first, plus C2 n equal to 1, so that give you only 2. Okay, in both cases, we replace the n by 1. So the result of the equation is going to be what? It's going to be 2c1 plus 2c2 equal to 3. Okay, this is going to be our second equation. Any question? But you already got, you know, if you want to put them into the system of two equation, two variables, you already got the C1. Okay, your C1 is equal to 1. So the C1 is equal to 1. You substitute here. So that gives you 2 plus 2C1, 2C2 equal to 3. Okay, I just put C1 equal to 1. So that will give us 2C2 equal to the 3 minus 2, which is equal to 1. So your C2 would be half. Okay, C2 would be half. Now we are going to be giving you the general solution. So what's going to be your general solution? Your AN is equal to, you see the AN is going to be equal to what? C1 times 2 to the n. C1 is equal to the 1. So it's going to be just 2 to the n. Okay, plus C2. C2 is 1/2. It's going to be 1/2. 1/2 times what? Times n 2 to the n. Okay, that's fine. Some people, they multiply the 1/2 inside. It's optional. So if you like it, you can write it down as, or some people, they factor out the 2n. It depends, you know, what you want to do. But this is done. You know, we accept it. We accept it as is or just any other combination. But you have to give us the range of the n. N can be 0, 1, 2, etc. So that gives you the general solution of your equation. Any question? So again, easy procedure. Make sure don't miss any sign, especially in this second part. I don't know why. You see the people, this is going to be of this kind of format. When they move this one to the other side, they usually miss a sign. They miss a sign. For example, they go with a positive here. So if it's going to be positive, then you have R plus 2. So everything would be different. So make sure, you know, double check when you move it to the other side. And you have to move it to the other side to be able to solve it. That's another thing that some people, you know, they miss it. Okay, any question? Now, all the examples are going to be in this form. You have 5 in your book and nothing to worry about. There is only one that is going to be popular one, the reason that we create this method, and that's a Fibonacci equation. I do it for you. It's just a unique one, so we are not going to give you probability on the test because it's a unique solution. And there are some algebra involved. I just want to know not to be surprised. But everything else must be nice. So if you try to solve that equation and you arrive at something strange, probably you miss something. You have to double check it, okay? So let's check the Fibonacci one. Very interesting example. So that's a Fibonacci case. We want to solve this equation to get the Fibonacci one. Any question? What's the question? To get these numbers. There will be a case when we have to deal with the imaginary numbers. Yes, of course, you can do that. Not in your case. No, not in your case. Imaginary number, you are not going to have one. You have one in your book, but not as a question. You see, for the imaginary one, this is your, let me see. You see, if you go to the imaginary one, I just, you know, give you this example. Let me just use another paper. You see the situation for the imaginary, you need a little bit of algebra. Imaginary solution is this one. You know that imaginary solution will be in the form of A plus or minus BI. This is going to be your solution. So in this case, you have two solutions, two distinct ones. You see, one of them is A plus BI, and the other one would be A minus BI. Then you can do the same thing. And the same thing is going to be, you know, that the solution would be what? You're going to get one r to the n here and r2 to the n. But the difficulty is going to be this one, a plus bi to the n. You see? You have to simplify it. If you are familiar with the complex numbers, you know that each complex numbers can be changed into the trigonometric form. So you have to change this one into the sine and the cosine. Okay, if you are familiar with the Morgan law, and then you simplify it to get, to get that numbers. If you are going to be, so the nature is going to be the same. You can leave it as is, you see. If you substitute it, you can leave it in the complex form, but you have to go on to get it. That's the difficulty. But no, officially you don't have it. Because in the application that you have, you don't usually use complex numbers. You just in real numbers. But in case you want to do it, if you are familiar, you know that this would be changing to the r cosine of the data plus I sine of the data from complex numbers. And that would be Rn cosine of the n data, sine of the n data. Then you can change it. Your solution would be in terms of the sine and the cosine. I can give you the solution, but no, it's not going to be the case. Okay, so just suspect that two solutions and the distinct and the repeated one. Okay, let's quickly check to see what is the difficulty with the Fibonacci one. You have a similar one. You have one of your assignments or of this form. Okay, we want to solve this linear equation. You see the linear relation. And the relation is Fibonacci. Fn equal to the Fn minus 1 plus Fn minus 2. Okay, in this case, n goes from 3, 4, etc. Then they give you the first term, F1 is 1, you know that. And the F2 is 1. Okay, so it's a recurrence relation of the second order. So we have to get the characteristic equation first. Solution. The characteristic equation is going to be, okay, characteristic equation for the Fibonacci one is you start with the r squared equal to, the coefficient is 1, just 1 times r, plus the coefficient is 1. So that would be your characteristic equation. Okay, you move it to the other side, r squared minus r minus 1 equal to 0. You have to solve this equation. You cannot factor it. You cannot factor it, you have to use quadratic formula to take care of it. Okay, for the quadratic formula, so a1 is 1, a1 is 1, b is a negative 1. The formula for the quadratic equation, I'll go with the discriminant first, delta or d is a b squared minus 4ac. So that give me negative b squared minus 4 times ac. A is 1, c is a negative 1. So that give you 1 plus 4, because negative would be positive. So that make it into the 5. It's positive. It's not a perfect square. Okay, so your solutions are going to be, you see, r is equal to negative b plus or minus the square root of delta over 2a, the quadratic formula. So this would be equal to, a negative bb is a negative 1, so it's going to be negative 1 plus or minus radical 5 over 2a, 2 times 1. Negative would be positive, so you arrive at this number. You get 1 plus or minus radical 5 over 2. You see, these are going to be your solutions. So you have two solutions. R1, which is 1 plus radical 5 over 2. This is going to be 1. The other one is going to be R2. R2 would be 1 minus radical 5 over 2. So these are going to be your two solutions that you have. Remember the golden ratio that we talk about it. This is the golden ratio. At the 1.6 something that I told you. Now the solutions are going to be distinct, but not nice. You are not going to use your calculator, of course. So what's going to be the general solution? The general solution would be Fn is equal to the remember C1 R1. R1 is 1 plus radical 5 over 2, everything to the n. Okay, plus C2 R2 to the n is going to be 1 minus radical 5 over 2, everything to the n. You see, this is going to be the case for, of course, n equal to the 1, 2, 3, etc. So this is going to be the general solution for the Fibonacci sequence, or the Fibonacci numbers. Okay, any question? But you are not done, because you have to find the general solutions. Okay, this is the general solution, but we have some. So this is the general solution. This is going to be the general solution, but you are not satisfied because you have some initial condition. What do you have? But f1 is equal to 1 and f2 is equal to 1. So what you have to do is you have to substitute these numbers and try to find the C1 and the C2. It's not easy, you know, it can be done, but it takes times, because if you put n equal to 1, you see, this is going to be, sometimes we modify it, we start with 0, it's easier, but if this is going to be the case, you see f1 is equal to 1, so that give you this equation, that give you C1, okay, C1, 1 plus radical 5 over 2, plus C2, 1 minus radical 5 over 2, equal to 1. So that give you one of the equation. Okay, and which is not a nice, you know, we can simplify it a little bit, but it can be done. And then you have the f2 equal to 1. If you get f2 equal to 1, then it's going to be what? It's going to be C1, n equal to 2. That's going to be 1 plus radical 5 over 2 squared. And this is going to be C2, 1 minus radical 5 over 2 squared. And this would be equal to 1 first. You see, that's going to be a system of two equations, two variables, that you have to solve it. It's not easy, but it can be done. If you solve it, the final, I just give you the final answer. So the final answer for the Fibonacci, if you want to keep it as a record, is this one. Fn is going to be, this is the format they write it down. It's going to be 1 over radical 5. Okay, and this is going to be 1 plus radical 5 over 2. After simplification, of course, it's going to be n plus 1 and minus 1 over radical 5, 1 minus radical 5 over 2 to the n plus 1. This is going to be the format of the Fibonacci numbers. Of course, you may say, oh, I know the Fibonacci numbers. The number is going to be 1, 1, 2, 3, 5, 8, 13. Yes, you replace n by 1. You replace n by 1, everything would be simplified, and at the end you get f1, 1, f2, 2, etc. Okay, but it's a lots of algebra involved to, you know, to get it. But we just want to confirm that this method is useful and enable you to find a general formula for the Fibonacci numbers. Okay, so as I told you, this case is very special because you're just proving something. But all the others that you're going to have, easy equation, you solve it, and you will get your result. Okay, so this is solving this relation, linear recurrence relations for the two. Any question?
This one like case one?
Yes, it's a case one, but it's an awful one. Yes. Yeah, it's a case one. Sometimes we simplify it a little bit. It's not going to be easy, and it is not bad, but because in your case is you have to use something like addition method to solve this system. And you know that you have to decide to eliminate one of these variables. So you have to make the coefficient to be the same as each other. So for example, this is the square. So you have to multiply the first one by 1 plus radical 5 over 2 so that we'll be able to eliminate the C1. Okay, it can be done, but this is going to be the case. Yeah, it's going to be the case 2. There are two types of numbers. This is Fibonacci. There is another one in your book they talk about it, but there are some other way to discover this to get to the Fibonacci case. Okay, so as you can see, it's a unique one, so it's no point to give you this one on the tests because we already solved it. So we give it two easy one with the repeated solution and the distinct one. Just use that idea, and you have 5 to check, and you already got 3 on your practice one. If you want to know more, the next step is going to be, you are not going to use it, of course, but in your book, in one of the problem at the end, they just give you some problems for fun or for advanced learning, if you like. This method can be extended, if you like. Okay, it can be extended to this is the second order. You can have the third one. Okay, so for example, you can have, just give you the idea, but I'm not going to do it. You see, for example, you can have something like this one. It's not the second order. You see, you can have something like AN. You start with AN, but then this is going to be something like 3AN. Just let's say AN minus 1. Okay, AN minus 1. Then you get 2AN minus 2. And then you may continue. You get something like 3AN minus 3. You see, this is of the third order. But you can use the same method to solve it. They have to give you 3 conditions. If you want to solve this one, your characteristic equation would be R cubed equal to, because you go up to the third. So then this is going to be R squared, and this is going to be the 2R, and then you get a positive 3 here. You see. Then you move everything to one side. You see, this would be your characteristic equation. And sometimes it's not easy to solve this one. But if you solve it, then you get 3 solutions. You get the R1, R2, and R3. If the solutions are going to be all distinct, okay, so if you get a distinct solution, so now your general solution would be C1, R1 to the n, C2, R2 to the n, C3, R3 to the n. You see, this is going to be your general solution. But if one of them is going to be a repeated one, okay, so if you have something like this is where it's a distinct. So if you have the R1 and then the R2 and the R3 happen to be the same thing. If this is going to be the case, we call this one R. So what's going to be your solution? AN would be, this is the distinct one, C1 R1 to the n. Then for this new one, as we did it before, it's going to be C2 R to the n plus C3 n R to the n. You see? We're just extending that idea from the characteristic equation of a second order to the characteristic equation of a third, and you can go on forever. But a couple of places that you are going to use it it's going to be of the second order. But that give you an idea. And in case you know, there is one problem in your book. I think it's even number right at the end. I haven't assigned that one for you. That they ask you to do it. It is general idea. Okay, that's it. This is section 5.8. So I give you introduction to the 5.9 a little bit, because if we can get it on this quiz would be better, so that if you want to make a mistake, you are going to make it on that quiz. And then I go over the review one, because we should have enough material to talk about it. So what is going to be this last section? Sometimes we drop it. We don't cover it, okay, even at university, but I always cover this one, because that is something that in fact you use in your field. So remember these ideas that I've got over here. These equations recursively defined is already given to you. Then you solve it. But your situation is going to be sometimes you may have to build something. You may have to build a mathematical modeling, if you like. So the way we do it in computer science is we start with the foundation. You see, if you want to build a building, so what do you need? You need a foundation. This is a foundation. If you have this foundation, you try to build, okay, the first floor. Okay. So you be given a foundation, you get the first floor. When you get the first floor, you get an idea. What did you do to get to the first floor? You do it again, you get to the third floor. Then now you get quite experience. Then you do it again. You get to the fourth one, and then you continue. So this type of ideas is going to be called a recursively defined, recursively defined set, if you like. So it's like the way we describe it is like, you know, you want to grow something. So what do you need? You need seeds. Okay, the foundation is the seeds, or you're growing a trees, if you like. So when you have the seed over here, okay, then for the tree, for example, this seed would produce something for you. So the way we refer to it, this is going to be a parent. The parent would produce a children, see, a child. Then the child by itself would be a new parent. So the child will introduce another children, and then you continue. You do it over and over and over. This type of procedure is called recursively defined set, and you do this type of action in computer science. So we're just going to show you what is the rules of this type of ideas. Okay, so I briefly talk about it, and it's very easy procedure. We have a couple of models to check, but it's quite interesting for you to get to it. So we may try something like 30 minutes on this one, and then we go over that review that are posted for you. Okay, it would be better to have this quiz covering everything chapter 5, because chapter 6 is going to be easy. We're just covering one section, set theory, and for the rest of the course, we are going to check going back to the relations, not the functions, and then we try to finish it. Okay, that's it. Any question? So get to know the problems that we did so far on the quiz. It can be done. And then I go with this idea, and we try. We are not going to push it. If you cannot finish it, we leave it. Then we give you the quiz on Wednesday. That's the target for next week. That's it. Any question? By that time, you will get your result. Okay. The test, I have 2 more tests to grade, but I start look at yours. Starting maybe tonight. Then you will see it when I grade it one by one. Okay. Any question? So that's it. See you on Monday for the review. Bye-bye.
See you Monday. Thank you.
Thanks, Professor.